Okay, so fusion power. It's like the holy grail of clean energy, right?
Yes.
What if we could, like, replicate the power of the sun right here on Earth?
Yeah,
Sounds kind of sci-fi, doesn't it?
it does.
Well, today's deep dive is gonna maybe take us a step closer to that.
Okay.
We're looking at a scientific paper about this cutting-edge fusion experiment. It's called SMART.
Right.
Now, I'll be honest, this paper is dense,
It is. It's pretty dense.
but we're going to break it down.
Okay.
And by the end, hopefully you'll understand why this little machine, it's being built in Seville, Spain.
Yeah.
Why this little machine just might hold the key to our energy future.
Well, and what's really fascinating about this is this isn't just like a theoretical paper,
Yeah,
this is a real machine that's being built.
it's really happening.
It's really happening. And this paper is kind of giving us a sneak peek at what it could do.
So no more of this like theoretical physics mumbo jumbo.
Yeah.
We're talking like tangible real world stuff.
Yeah, we're getting into like the nuts and bolts here.
I like it. All right. So for those of us who aren't, fusion scientists,
Right.
let's start with the basics.
Okay.
What is SMART?
So SMART stands for Small Aspect Ratio Tokamak.
Okay.
And a tokamak is basically this device that uses these super powerful magnetic fields to contain this superheated gas.
Okay.
And we're talking millions of degrees Celsius.
Oh, wow.
And that gas is called plasma.
Okay.
And that plasma is where the fusion reactions happen.
So we've got our superheated plasma soup cooking away in this tokamak. What makes SMART's design different?
All about the shape. So imagine your classic donut shape. That's kind of your typical tokamak.
Okay, a donut.
SMART takes that donut and it kind of like squeezes it.
Okay,
So the hole in the center is proportionally larger.
got it.
They call that a small aspect ratio.
Okay.
What's even more interesting is they've also shaped the plasma into like a slightly triangular form. It's a feature called negative triangularity.
Okay, so instead of a donut, we've got like a triangular bagel here.
Yeah, kind of, yeah.
I kind of wish we had visuals for this.
I know, me too.
But seriously, why go through all that trouble to reshape the plasma? Like, what's the point?
Because this really unique configuration could be like a game changer for fusion power. You see, because this compact triangular plasma, it might actually be way more efficient at like confining the heat and energy.
Oh, okay.
And that could potentially lead to smaller and cheaper fusion power plants in the future.
Okay, now we're talking. Smaller, cheaper fusion power plants.
Exactly.
That's the dream.
That's the dream, yeah.
But how do we get this triangular plasma cooking hot enough for fusion to actually happen?
Well, that's where things get even more interesting.
Okay.
This paper, it really dives deep into this thing called phase 2 of SMART's operation.
Okay.
And that's where they incorporate this super powerful heating method called neutral beam injection.
Okay. NBI.
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 NBI. So break it down for me.
Okay.
What is neutral beam injection?
Oh.
So imagine you're aiming like a fire hose of high-speed particles directly into the heart of this crazy hot plasma.
Okay.
That's basically NBI in a nutshell.
Okay.
Like you're giving this plasma this massive energy boost.
And this energy boost is crucial for actually getting us to fusion, right?
Yes.
Because we need things to get extremely hot, right?
I mean, it's super hot.
Yeah.
We're talking hundreds of millions, even billions of degrees Celsius.
Wow.
Yeah, to put that in perspective, that's hotter than the core of the sun.
Oh my gosh.
Yeah, it's mind-blowing. And this paper suggests that NBI could be the key to reaching those temperatures in SMART.
Wow. Billions of degrees. That is mind-blowing. But hold on a second.
Yeah.
I'm guessing it's not as simple as just like blasting the plasma with this particle fire hose.
Right.
Right? Like aim has to matter, right?
You're absolutely right. Yeah, it's not just about raw power. It's about precision. It's like, when you're trying to toast the perfect marshmallow.
Okay, yeah.
You get too close to the fire, it's like, boom, instant charcoal.
Right, goes right up in flames.
Too far away, and it's just like, never gets gooey.
Yeah, you want that perfect golden brown.
Exactly. You need that sweet spot.
Okay, I can see where you're going with this. So finding the perfect aim for this particle beam, that's got to be super critical.
Absolutely. And the paper, they spend a lot of time on this thing called the tangency radius.
Okay.
And basically what they found is that if you aim the beams just a bit off-center, like about 44 centimeters out from the center of the plasma,
Okay.
that's where you get the most bang for your buck, so to speak.
So it's all about maximizing how much of that beam actually gets absorbed by the plasma.
Exactly. It's all about that absorption, getting that energy where it needs to go.
So, okay, they found the sweet spot. They're aiming it right. But how does that translate to actual heat? This is where I imagine the numbers get really exciting.
Well, yeah, we're talking serious heat here.
Okay.
The simulations they ran, they suggest that with NBI, you could boost the ion temperature of this plasma in SMART to almost 1 billion degrees Celsius.
1 billion degrees.
1 billion. And get this, that's 5 times hotter than what they think they can get without it.
Okay, so let me get this straight. 1 billion degrees Celsius.
That's what we're talking about, yeah.
To put that into perspective,
It's mind-boggling.
that's mind-boggling. I'm starting to see why fusion is like the holy grail of energy, right?
It's incredible, isn't it?
But this paper, it doesn't just stop at like peak performance, right?
No.
It like simulates the whole process,
I mean,
right?
it's really cool, actually, because they looked at the whole shebang from the very beginning when you start the plasma all the way to, like you said, that peak performance.
Yeah, wow.
They even looked at how the very edge of the plasma, like the outer layer of our metaphorical sun here,
Right.
how that affects things.
So it's like realizing that every little detail, even the things you might not think really matter that much, can actually have a huge impact.
It's like, how they say, like with baking, even if you preheat the oven differently, it can change how a cake turns out.
Right,
It's those little things. And this is showing us how everything is just so interconnected in this system.
Okay, so we've got our perfectly shaped plasma. We're blasting it with this precisely aimed particle beam, and we're paying attention to every little detail. But, and I hate to be a downer here,
Yeah.
but I have a feeling achieving fusion is not just smooth sailing.
Well, you're right. It's not easy.
Yeah.
Fusion it's a beast.
Yeah.
And one of the biggest things they talk about in this paper is this whole issue of instability.
Oh, okay.
And they refer to these as MHD events.
MHD events? That sounds kind of ominous.
A little bit, yeah, a little bit
Yeah.
sci-fi, but basically,
Okay.
think of it like you're trying to hold a beach ball underwater,
Okay.
It's like
Yeah.
it takes constant effort.
Right.
And the slightest little wobble,
Yeah.
and whoosh, it's like out of control.
Yeah.
Fusion's kind of similar. Even if you have this perfectly aimed NBI setup, you do everything right.
Right.
The plasma itself, it can still get all wobbly.
Oh. Okay.
And these instabilities, these MHD events, they're like those sudden wobbles.
Got it.
And they can just throw the whole party off.
Okay, so it's like we're trying to like orchestrate this perfectly synchronized dance, right?
Exactly.
But all the dancers keep like tripping over their own feet.
It's a good analogy, yeah. These things are tough.
Yeah. So how do they deal with these instabilities? Like, do they just cross their fingers and hope for the best?
Well, not exactly, because remember, SMART, it's not just about, like, making fusion happen. It's about learning how to make it happen.
Right.
So part of its whole mission is to understand these MHD events better,
Okay.
so that hopefully we can design ways to, like, avoid them altogether, or at least, like, lessen their impact,
So it's about like taming the plasma beast, one MHD event at a time.
Yeah, exactly. Learning how to predict and control it.
That's pretty amazing. Now, we've thrown around a lot of terms here. Negative triangularity, tangency radius, NBI, MHD events.
And that's a mouthful, right?
It is. So before we wrap up, can we just like take a step back and do a quick recap? What are the big takeaways from this paper?
Okay, yeah. So basically, you've got this super cool cutting-edge tokamak, SMART, right? It's got this unique triangular shape for its plasma, which is wild. Yeah. And they're using this powerful heating method called NBI, aiming it just right to crank that plasma up to, like you said, 1 billion degrees.
It's incredible.
It's mind-blowing. And they're looking at every little thing, every little step of this process to understand how to control it.
And this is all happening right now. Like, this isn't some distant future, right?
Exactly. This is research that's happening right now.
That's so cool. It really does feel like we're on the verge of something huge here, like something groundbreaking.
It really does, yeah.
And, this paper, it focused a lot on this, like, negative triangularity design for SMART, right?
Right.
But it got me thinking, like, what if there are even better shapes out there? Like, are we just scratching the surface here?
Oh, that's such a good question.
Yeah.
Like, who knows what other kind of amazing, weird shapes are out there that we could use? We've just found one that seems to work really well so far.
Right. We just need to keep exploring.
Exactly. And this kind of research, that's how we're going to unlock those answers and hopefully, get us to that future powered by fusion.
A future powered by fusion. That's something worth striving for, I think.
I agree.
Well, on that note, that's all the time we have for today's deep dive into the world of SMART and NBI. Until next time, keep those minds curious, everybody.